So what I've got here is just a simple circuit board, and we're going to just run off of a relatively low value resistor. It's just 10 ohms. If you really get into electricity, if you want to be an electrical engineer, if you look on these resistors, there's 4 different colors of bands, and there's a magic code that tells you there's a book it's a code that says, okay, based upon these colors, it tells you what that resistance is. So instead of saying, oh, it's a 10 ohm, so if you know the magic code, you can look at the sequence of this color and realize, oh, that's a 10 ohm resistor. So this sequence here is different from this one over here, which is like a 68 ohm resistor. And then you've got this really big one over here, which is a 100,000 kilo ohm resistor. Okay, so that's got a tremendous amount of resistance. So what we're going to do is we're going to look at this relationship. So what I have hooked up here is an amp meter. So is my amp meter hooked up in series, or is my amp meter hooked up in parallel? What's an easy way to tell?
It has to be
In
direct,
series.
because it's the only way the charge can flow through.
If you unplug it, does everything turn off?
Bingo. Okay, that's simple. Your answer is right, but he's got the answer that I want. So if I turn this up, okay, and this is a variable power source, and I've got it set on the DC side, and so right now I'm at about 0.1 amps. So if I disconnect this, it drops out. Nothing's happening. So my current goes to 0. So what this means is that, and this is the old style of amp meters, but chemistry and science and physics tends to hold on to the old school ways. So what I have here hooked up in series, so the electricity is flowing through here. The old style, Ben Franklin version of this, is that I've got the red positive, and the positive charges in that conventional sense are going from here, through here, boom, around to the negative side. And we're using up some of that electricity. So this is set up in series. Now, the current, write this down, so I is going to be 0.10 amps. Okay? No. Cool. Now, what I need to measure is the voltage drop across the resistor. Okay? So when you talk about voltage, which means, and it's going to say, it might say, hey, what's the potential drop? But we're not going to say what's the potential energy drop, because potential energy is measured in what? Joules. This is in volts, which is joules per coulomb. So this is the old style. Now, I'm going to hook this up in parallel. So basically what I'm going to try and figure out is how much energy is lost, how much food is consumed when those electrons are forced through that resistor. So now if you ever do this and you just hook this up across like this, and then you go over here. Now, if you do that, and this is what's happening here, and the voltmeter has sunk down into the negative region. If it sinks down into the negative region, there's a simple remedy. All you have to do is just reverse it, and then if you do that, then it should read up onto the higher values, okay? So literally, if you ever hook up a voltmeter and you get, oh, I've got negative numbers, just switch the leads. That's all you have to do. So right now, I've got a voltage of about 0.08, okay? .08. Yep, call it that. So if I just had those numbers, could I determine the value of the resistor? Yeah, what would I have to do? Math. Vert it up, right? So we write that down. So we're going to vert it up. So write down vert. Vert, V equals IR. And to solve for resistance, I'm going to do what? I'm going to take voltage and divide it by I. So I'm going to have V over I equals R. It's a pirate thing. So I got 0.1 divided by 0.08. I get a little bit more than 10. Okay? All right? So I get an idea of what that resistance is. Now, what I'm going to do is I'm going to increase the amount of current. Okay? So my new current, I'm going to bump that up to 0.2. Okay? So new current, 0.2. But my voltage, now without looking at that, do you think my voltage has gone up or has my voltage gone down? Or has my voltage just stayed the same? Up, why?
Because there's only two things, like if current goes up, your voltage has to go up because you're not changing your resistance.
Bingo. So the value of the resistor is going to stay the same. So if you VER it up, and if your resistor, which is basically a 10 ohm resistor, so if my resistor is staying the same, which it is at about 10 ohms, then if I put more current through it, then by contrast to that, the voltage has to go up. Okay, because mathematically that's the only way that can work. So I bump my current up to about 0.2, and this one up to about, also up to about 0.2. Okay, so both of them are at about 0.2, or excuse me, 0.02. No, I'm sorry. Yeah, back that up. So my current is 0.2, and my volts are about 1.6, okay? That should be 0.2 on your amps. My bad. I told you the wrong number. It's 0.2. Just move the decimal place. Move the decimal place. You're fine. Okay? So notice that that's kind of staying about the same ratio. So my amps about doubled. My voltage about doubled. Hey, we're staying about the same. So here's the whole point of this. This is what's known as an ohmic resistor. If your current and voltage change at the same rate, that's what's known as an ohmic resistor. Now, but there's a limit to that. Because, and I'll show you what happens in just a second if you have an extreme resistor. So that relationship holds as long as the temperature stays relatively cool. If the temperature goes up quite a bit, the molecules, the atoms inside begin to vibrate a lot more, and then that resistance goes higher because of the fact that it's just like, oh my God, it's harder to get that current to flow through. Quit putting things in his job.
Jacob put it on.
Now, in an extreme case, speaking of extreme cases, so
That's not.
put this off.
Huh?
Just stop talking.
There was a pencil here.
It's right there.
Okay, so we're going to try and force electricity through a substance that doesn't want to have electricity forced through it. So graphite isn't a very good conductor of electricity. It's made of electrons, protons, and neutrons, just like copper is, but on an atomic level, the electrons don't want to drift, okay? They want to stay locked up. It's hard to get an electric field to go through it. So let's even look at the here. We'll probably measure the amps while we're doing this, since we have that handy. Let's go up to 15. Boom, here we go. So I hook this up. And I've got the two wrong. There we go. So I crank this up. Now, I've got this cranked up almost about as high as it can get. With that 10 ohm resistor, I didn't have to have very much electricity at all to get that to flow through because the 10 ohm resistor is pretty low. So right now, I've got a current of about 0.35, and if I measure the voltage across there, my voltage is at about 10, okay? So I've noticed on this one, I've got a current of 0.3, I've got a very high voltage. Now, if you're somewhat close, you can kind of begin to smell a little bit of a burnt smell to it. Because what's happening is that this is, we're forcing that electricity through it, and it doesn't want it. Now, if I go all the way, you'll notice that it's actually starting to smoke. Because we're forcing so much, and then you'll notice here the lead actually is starting to begin to like boil, okay? Or the paint on the outside is beginning to boil. So, ooh, that was strong. Woo, okay, yeah, we're about on fire. Okay, so, woo, smoke signals, woo. So, what happens there, and this is like the classic example, is that if that had been a light bulb, that's basically how light bulbs work. The old incandescent light bulbs work. Because you would force so much electricity through it, because it had such a high resistance, that instead of smoke and heat, you would produce light. But unfortunately, you waste so much energy forcing it through, and then the byproduct produces so much heat. That's why they're so inefficient. So this is why the whole argument for this switch over to LED lights, because you get light and you have very, very little loss in terms of heat. So that's what happens, still warm, in the extreme case. Okay, back we go.